Class 11th Chemistry, Unit 2, Structure of Atom. In this video, we will discuss about quantum mechanical model of atom and quantum numbers. First come to quantum mechanics. The branch of science that takes into account the dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of the motions of the microscopic objects that have both observable wave-like and particle-like properties. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Fundamental equation of quantum mechanics was developed by Schrödinger, and it won him the Nobel Prize in Physics in 1933. The simplest form of Schrödinger equation is this: H psi is equal to E psi. This is called psi, and this is wave function. E is the total energy of the system, and this H is the mathematical operator, and this is called Hamiltonian operator. Solution of this equation gives E and psi. Dear student, at this level we are only discussing the simplest form of Schrödinger equation. Its solution is very difficult and it requires the high level of mathematics and quantum physics. Okay. Hydrogen atom and the Schrödinger equation. When Schrödinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions, that is psi, of the electron associated with each energy level. Wave function, that is psi, describe the orbitals which are characterized by a set of three quantum numbers, that is principal quantum number, azimuthal quantum number, and magnetic quantum number. We will discuss later on about these quantum numbers. Important features of the quantum mechanical model of atom. The energy of electrons in atoms is quantized, that is, only have certain specific values. The existence of quantized electronic energy level is a direct result of the wave-like properties of electrons and are allowed solutions of Schrödinger wave equation. Both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. Only probability of finding the electron at different points in an atom is considered. You can say this is the main point of this quantum mechanical model of atom. That is, we can't find out the exact position of the electron. We simply tell about the probability of finding the electron. An atomic orbital is the wave function psi for an electron in an atom. Whenever an electron is described by a wave function, we say that the electron occupies that orbital. The probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function, that is psi square at that point. And the psi square is known as the probability density and is always positive. From the value of psi square at different points within an atom, it is possible to predict the region around the nucleus where electron will most probably found. Now come to the orbitals and quantum numbers. Orbitals are described by a set of three quantum numbers which are obtained from the solution of Schrödinger equation, and these are principal quantum number, azimuthal quantum number, and this is magnetic orbital quantum number. To describe an electron, one more quantum number is required which is not obtained from the Schrödinger equation, and this quantum number is proposed by some another scientist, and that is electron spin quantum number. Okay, simply we can say actually this quantum number, in simple way we can say quantum number give the address of an orbital or address of the electron in an atom. First come to the principal quantum number, which is represented as n. It is positive integer with value of n is equal to 1, 2, 3 and so on. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species means uni-electron species having only one electron like He plus, Li2 plus, etc. Energy and size of the orbital depends only on value of n. The principal quantum number also identifies the shell and are represented by the following letters. If n is equal to 1, it is K shell. If this is 2, this is L. N is equal to 3, this is M. If n is equal to 4, this is N, and so on. With the increase in the value of n, the number of allowed orbital increases and are given by n square. We can say number of orbitals, not orbit. Number of orbitals in a given shell is given by the formula n square. The energy of the orbital will increase with the increase of n. And the maximum number of electron in a shell is given by the formula 2n square, where n is 1, 2, 3 and so on. Next come to the azimuthal quantum number represented by small n. Again remember, not capital L. This is small l. Capital L represent one of the shell. Okay, and small l represent the azimuthal quantum number. It is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. It identifies subcells or sublevels in a given shell. Simply we can say that is principal quantum number identifies shell and azimuthal quantum number identifies subcells in a shell. The number of subcells in a principal shell is equal to the value of n, and the possible values of L are 0, 1, 2 and this is up to n minus 1. The subcells corresponding to different values of L are represented by the following symbols. You can say if value for L is 0, then notation for subcell is S. If this is 1, then this is P. If this is 2, then this is D. This is 3, this is F. This is 4, this is G. This is 5 and H. Simply you can say these subcells are represented by this is S, P, D, F, G, H and so on. Okay, and these subcells also have the fixed value. S is always have 0. P is always 1. D is always 2. F is always 3. Maximum number of electrons in a given subcell is given by the formula 2, 2L plus 1, where L will be these values. Okay. If we put value of L 0, then we can find out that in S subcell number of electrons will be 2. If we put the value of P1 in that formula 2, 2L plus 1, it will come to 6. In the same way, in D subcell, maximum 10 electrons, in F subcell maximum 14 electrons, in G subcell maximum 18 electrons and in 22. Okay, in the same way we can find out. Now these subcells also have the specific shape. S subcell is spherical, P is dumbbell, D is double dumbbell and F is complicated, and about these shapes we will discuss in the next video. Now this table indicates the principal quantum number along with the azimuthal quantum number. Okay, just try to understand. These are the values for the principal quantum number, that is n, and these are the notations of the cell. Okay, now we can find out number of subcells in a shell which is equal to value of n. If this is 1, then there is a 1 subcell, and this one subcell has the value of 0. How this 0? Because value of subcell will start from 0 and this will end to n minus 1. Okay, that's why this is the first shell. N is equal to 1. That's why 1 minus 1 is equal to 0. And this 0 subcell is represented by S. Okay, and this subcell is present in the first shell. That's why this is written first. This first represents the principal quantum number, and this S is the notation for subcell. Is it clear? And number of electrons Okay, now this is the S subshell, that's why number of electron is 2, and this can be calculated by using this formula. The same way, if n is equal to 2, that is L shell, there are the two subshells are there. Okay, now these subshells have the value of 0 and 1, and for 0 the notation is 2s, and for 1 this is 2p. Actually, this for 0 notation is s, and for 1 notation is p, but this s is present in the second cell, that's why we'll write it 2s. Okay, and this p is present in the second cell, that's why this is 2p. Again, by using this formula, we can find out the number of electrons. As subshell, always maximum electrons are 2. In p, this is 6. And if we add these two, then we can say there the 8 electrons are present in the second cell, which can also be found out by using this formula 2n square. If n is equal to 3, this represents the m shell, and number of subshells in third shell are 3, and their values are 0, 1 and 2. 0 is for S, 1 for P and 2 for D, and these subshells are present in the third cell, that's why this is 3S, 3P, 3D. And in these number of electrons, in 3s 2 electron, 3p 6 electron, 3d 10 electron. Okay, if you add, we can find out 18, maximum 18 electrons are possible in the third cell. In the same way, if n is equal to 4, this is capital N. Okay, and subshells are again 4, and these subshells have the value of 0, 1, 2 and 3, and the notations are for 0, S for 1, P for 2, D for 3, F, and these are present in the fourth shell, that's why these 4 is written. Okay, and number of electrons 2, 6, 10 and 14. As subshell have 2 electron, P 6, D 10, F 14, and whatever the cell in which they are present. Okay, in this way fourth cell has 32 electrons. Now next come to the magnetic orbital quantum number, that is ML. It gives information about the spatial means space, a spatial orientation of the orbital with respect to standard set of coordinate axes. Number of orbitals in a given cell is given by the formula 2L plus 1. Okay, where L is again 0, 1, 2, 3 and so on. These are the number of orbitals. Then values of ML for these orbitals will start from minus L, passing through to 0, and this will go to plus L. Okay, we will discuss this, how these values we will assign to these orbitals. And maximum number of electrons in an orbital will be equal to 2, and number of orbitals in a given shell is given by the formula n square. Now see value of L, that is subshell. These are the values of subshell, and the notation of this subshell are for 0, this is S, for 1, this is P, this is D, this is F, G and H, and number of orbitals. Okay, number of orbitals we can find out from this formula 2L plus 1. If we put the value L is equal to 0, number of orbital in S subshell is 1. In P, L is equal to 1, 2 into 1 plus 1, that is 3. 3 orbitals are present in P subshell. The same way, 5 orbitals are present in the D subshell. 7 orbitals are present in the F subshell, and so on. Okay. Now, see this table again. This is N, subshell is 0, and this is 1s. In this case, number of orbital is 1, and this value is 0. Okay. Why 0? This value is starting from minus L to 0, and this will go to the plus L, and for S subshell value is 0, that's why for orbital ML value will also 0. Now this is again 2s. Okay, 2s, that is again this is S subshell, there is a 1 orbital is there, and its ML value is also 0. Now come to this one, that is this is P subshell. In P subshell 3 orbitals are there. Okay, and these orbitals, 3 orbitals, and for the P the value of L is 1. Okay, that's why these 3 orbitals have the value of ML is minus 1, 0 and plus 1. Okay, these are the. The same way, this is 3s, there is one orbital, value of ml is 0. 3p, there is a 3 orbitals are there, value is -1, 0, +1. Now again come to this d. Okay, d subcell have 5 orbitals. Okay, now what are the ml values of these 5 orbitals? Now for the d, value of l is 2. That's why we'll start from -2 and this will end to +2. -2, -1, 0, +1, +2. In this way, again come to the f. 7 orbitals are there. Okay, and the ml values of these 7 orbitals are again value of l for f is 3. That's why we'll start from -3 and this will end to +3. -3, -2, -1, 0, +1, +2, +3. Clear? Now again see, each orbital in an atom is defined by a set of values for n, l and ml. An orbital described by the quantum number n is equal to 2, l is equal to 0, ml is equal to 0 is an orbital in the p subcell. It means if these values are given, we can identify that which orbital and what is the subcell and shell of that orbital. So you can see n is equal to 2. It means this orbital is present in the second cell. And L is equal to 1, that is in second cell, this is present in the p subcell. Okay. Now next one is the electron spin quantum number. Now again remember, to describe the orbital, we required only 3 quantum number which we have already discussed. And to describe the electron, we need one more quantum number. That is total 4 quantum numbers are required to describe an electron. And it's represented as ms. In 1925, George Annelbeck and Samuel Goldsmith proposed the presence of 4th quantum number known as electron spin quantum number. As we know, an electron spins around its own axis. Spin angular momentum of electron, this is a vector quantity. Spin angular momentum is a vector quantity, and this spin angular momentum of electron can have 2 orientations relative to the chosen axis. That means this motion of this spin, it may be clockwise or it may be anti-clockwise. That's why 2 orientations are possible, and these 2 orientations are represented by the spin quantum number ms, which can take the values of +½ or -½ These are called the 2 spin states of the electron and are normally represented by 2 arrows. Upward arrow, that is spin up, and downward arrow, that is spin down. So you can say this is +½ or -½ or upward arrow or downward arrow. 2 electrons that have different ms values, that is one +½ and other is -½ are said to have opposite spins. An orbital cannot hold more than 2 electrons, and these 2 electrons should have opposite spins. This is about electron spin quantum number. Now again see, this is the summary whatever we have discussed. Again see, this is okay. First of all, you see this. This is the brief summary. Number of subcells in a cell is equal to value of n. Number of orbitals in a shell is equal to n square. Number of orbitals in a subcell is given by 2l plus 1. Okay. Number of electrons in an orbital 2. Number of electrons in a subcell is given by 2l plus 1. Number of electrons in a shell is given by 2n square. Now just see values. For principal quantum number, this is 1, 2, 3, 4 and so on. For azimuthal quantum number, that is L, this is from 0 to n minus 1. And for ml, this is minus L passing through 0 and end up to plus L. And for spin quantum number, +½ or -½ Now again you can see this table. This n is equal to 1, K shell, there is 1 subcell is there having the value 0, and this is 1s. 1s subcell has 1 orbital, and that is again represented by the 1s, and this orbital have 2 electrons with these 2 spins, +½ and -½ and these are the total number of electron in one as orbital or one as subshell or first shell. Okay. Now in case of second shell, there the two subshells are there, 2s and 2p. Again this is as value of L is 0, for the p this is 1, and this is as it has only one orbital, that is 2s. Okay, and its value is ml value is 0, and again two electrons are there with plus half and minus half spin quantum number. Two electrons are present in the 2s orbital. Now 2p subshell have three orbitals, and these are designated as 2px, 2py and 2pz. Actually p subshell has three orbitals, px, py and pz, and this p subshell belong to the second shell. That's why we are writing 2px, 2py, 2pz, and their values are from -1 to 0 to +1. Again remember student, this -1, +1, 0, they are not having any direct relationship with the px, py and pz. You can say any value with any orbital you can put it. Okay, and again each orbital have two electrons with opposite spin. These are plus half and minus half. In this way total 6 electrons are present in the p2p subshell, and you can add then the 8 electrons in the k shell. In the same way, third shell k, 3 subshells are there, 3s, 3p and 3d. Their values are values of L, that is azimuthal quantum number, 0, 1 and actually this is wrong, this is 2. Okay, and then in this subshell one orbital is there, this is 3s orbital, 2 electrons are there. Okay, and this is 3p subshell, again has 3 orbitals, 3px, 3py, 3pz, and each orbital has 2 electrons with 2 opposite spins, plus half and minus half. In this way 3p subshell has 6 electrons. In case of D subshell, there the 5 electrons are there. Sorry, 5 orbitals are there, and their designations are these. We also discuss these designations when we will discuss the shape of these orbitals. This is 3dxy, 3dyz, 3dzx, 3dx squared s y square, and this is 3dz square. Okay, these are the 5d orbitals, and each orbital has 2 electrons with opposite spin, plus half and minus half. In this way total number of electrons in 3d subshell 10, and if you add these 2 plus 6 plus 10, so we can say that is 18 electrons are present in the third shell. Is it clear? In the same way you can find out for n is equal to 4. Now see some questions. What is the total number of orbitals associated with the principal quantum number n is equal to 3? When n is equal to 3, number of orbitals in a shell is given by the formula n square. Put the value n is equal to 3, we can find out 9. Now how these 9 orbitals are present? When n is equal to 3, number of subshells are 3, and these are 3s, 3p and 3d. Okay, and number of orbitals in a subshell is given by the formula 2l plus 1, and for value of L, for s this is 0, for p this is 1, and for d this is 2. If we put the value, then we can find out number of orbitals in 3s subshell is 1, in 3p subshell 3 orbitals are there, in 3d subshell there the 5 orbitals are there, and if you add you will get the total number of orbitals if n is equal to 3 is 9. Using SPDF notations, describe the orbital with the following quantum numbers. Okay, you have to designate the orbital if they having these quantum numbers. If n is equal to 2, L is equal to 1, it means this is the second shell, and L is equal to 1 means P subshell. That's why this is 2P. In the same way, n is equal to 4, L is equal to 0. 4 is the principal quantum number, that is shell, and L is equal to 0, it means it is representing as subshell. That's why this is 4s. If n is equal to 5, L is equal to 3, and this is 5f. If n is equal to 3, L is equal to 2, this is 3d. Yes, friends? Thank you.